Hello guys, we're going to solve systems of equations today by substitution, and we're going to start with this little warm-up for you. Still looking at solving quadratics, figuring out what x needs to be to make these equations with x squareds true. Okay, so go ahead and take a second and solve those. And remember, you can press play or whatever when you're done. On this guy, our best bet would be, it is nice, easy, kind of manageable numbers. While it's not wrong to complete the square, it will be best if you do factor, and 3 and -5 will be the factors we will use. If you have something in factored form, that's really nice because it allows us to use the zero product property and solve quickly. So x will have to be -3 because that would make this guy 0. And since it's multiplying by this next guy, to make it 0, it would have to be 5. On the second problem, you can already get x by itself. You don't want to expand it. You don't have to. You can just go straight to square rooting both sides. Don't forget your plus or minus. So that would be x plus 5 is plus or minus the square root of 24. The square root of 24 does simplify. That's 4 times 6. So that's 2 root 6. So x plus 5 plus or minus 2 square root of 6. And if you get x all by itself, you would subtract 5 and you get -5 plus or minus 2 square root of 6. So your two answers would be -5 plus 2 square root of 6, which is a nasty decimal, and -5 minus 2 square root of 6, which is another nasty decimal. Now, how would you solve this last quadratic? Okay, frequently when I give problems like this and I tell kids to solve, they want to FOIL or double distribute and do crazy stuff. But no, this is factored form. This is no different than when we factored. We can do the zero product property. This times this equals 0. So each one of these factors can equal 0 and we can solve. So 3x plus 1 could equal 0, or x minus 4 could equal 0. And the second one is definitely easier. X would equal 4. This one you will have to math a little bit. You subtract 1 from each side and you get 3x is -1. Divide both sides by 3 and x is -1/3. So the answers to this guy are -1/3 and 4. So we got two answers on all those quadratics. We solved by factoring this one, and this one was, they call it the square root method. So we said get x by itself, and the last one we also solved by factoring. So we're going to solve systems by substitution today. This should be kind of a review for you, but we're going to go back in time and talk about our other methods first. We use the word substitution in math, but kids frequently like to use the word plug in instead. Oh, just plug it in. So what does that mean? Well, when you substitute a value for x or y, are we solving it? Are we eliminating it? Or are we temporarily replacing it? When you substitute, you temporarily replace. We plug something into the equation. So we plug in a number for x or a number for y. Given the equation y equals x minus 2, you substitute 5 for x. So if I substitute 5 for x, what will happen here? X will temporarily be replaced with 5. True, because it doesn't always be 5, but right now we're doing that. The equation would then become y equals 5 minus 2. That's true. And that would make y equal to 3. Also true. Is this equation no longer true? No, it's still true. We just substituted 5 there, so that's not right. It's still true. It just has a specific value assigned to it, and that's also correct. When you make an XYT table, you substitute lots of values in, and the equation is still true. We're just giving specific values to it. What if it says you substitute 3 for y this time? What if you put 3 in the y spot? You would replace y with 3 temporarily. Is it wrong? Can you only substitute for x? No. You can still substitute for y. We just usually substitute for x when we make an XYT table, so it might not be as well practiced. The equation would then become 3 equals x minus 2. And does x equal 5? Well, if you get x by itself, you would add 2 to both sides, and sure enough, it does equal 5. It is still true, just with specific values. So when we're plugging things in, remember, that's just a common way of saying substitute. All right, so when we say equations are satisfied, that means that it means it's true. So if we have this equation x minus 2 and you look, they graphed it for us. When x equals 5, 1, 2, 3, 4, 5, y equals 3. It satisfies the equation because it makes it true. Satisfies means makes it true. So when y equals 3, 1, 2, 3, and x equals 5, that's the exact same way of saying it satisfies. So xy equals 5, 3 satisfies that equation because it makes it true when you substitute both x and y at the same time. You have to substitute them both for the whole point to work out. If there are infinitely many points to the equation y equals x minus 2, those are all the solutions, okay? That's all the solutions that make it true. But multiple points, all of these points with dots, satisfy the equation. But they're not the only answer. The only answer shows up when you're looking at a system when there's two lines at once potentially. You would want something that would satisfy them both at the same time. And that's what this is talking about. So while one line has infinitely many answers and the other line has infinitely many answers, there's only one point, and that point is 5, 3 here, that would satisfy both of these lines. So recall that a solution to a system is when they're both true, when you substitute. So if we plug 5, 3 in to this first equation, x minus 2, y-intercept negative 2, slope of 1, we plugged it in, we already did that. We had 3 equals 5 minus 2. It's true, it satisfies it. This guy that they graphed in purple, you may not even know that they graphed it because they did not get y by itself. So I'm going to get y by itself first. It'll be 3y is negative x plus 14. Divide all the friends by 3, and you get y is negative 1/3 x plus 14 over 3. You might not have even told this is 14 over 3 is a y-intercept. When I will plug 5, 3 in or substitute it in, this is not the best place to look. I believe that the graph is right now. You have this point. The slope is negative 1/3. It went down 1 over 3. Still in the middle there. That's a full down 1 over 3. I believe the line is correct, but when I check to see if it's satisfied, it will be easier for me to go to the standard form. Plug in x is 5, plus 3 times 3 is 5 plus 9 equal 14. Sure enough, it satisfies both equations. So systems are satisfied when you find the solution. We're going to solve systems of two variable linear equations using substitution today. Okay, so how do we use substitution? Well, what we do here, we use substitution when you have a fact. One variable is what we call isolated. So this y is isolated to x minus 2. So it's like $1 is 4 quarters. We talked about how powerful the equal operator is before. If y equals x minus 2, and these two guys are going together, every single time you see a y, if I want, I can put x minus 2 in its place. Instead of paying with $1, I can pay with 4 quarters because it's the same. So when I see this y right here, instead of writing the y, I can in parentheses put x minus 2 because it's the same thing as y. Now, why would I want to do that? Because now I only have one variable, and you can solve for one variable. We would distribute, and we'd have x plus 3x minus 6 equals 14. You'd clean up a little bit. That's 4x minus 6 equals 14. You would solve for x. 4x equals 20, and x equals 5. So we solve for one or the other in x or y. You get one isolated. Well, it was already isolated for us. We substituted the expression in, and we solve for one of the variables. After you do that, we back substitute, and we solve for the first variable. You can pick which equation that you'd plug it into, the top or the second. It will be easier to plug into this bottom one. Y is just 5 minus 2, which is 3. So we were able to use these together by using substitution and putting one to the other to figure out that the point 5, 3 satisfies both of those and is the solution to the system of equations. Let's try it again. What if a variable is not isolated? Well, if you want me to be completely honest, if a variable is not isolated, I prefer to use elimination. If it was me and I was assigned this problem on a homework problem, I would multiply the whole top by -2 and do elimination because that's my preferred method. Today, I do want everybody to practice with substitution. So we are going to use substitution even if you would rather not. But on your test, if it was lined up like this and you chose to use elimination, that would be fine. If it's not isolated, you will have to isolate. So you'll look at both equations and say, is it easy to get one of these variables by itself? And it is. It's easy to get x by itself in the first one. All I have to do is subtract 6y. So I have 29 minus 6y equals x. Is it wrong if you say negative 6y plus 29? No, a lot of kids like to do it that way. It's perfectly fine. So now that I have one isolated, now, since this is the equation is the same as that, I can use my fact and substitute this wherever I see an x. So wherever I see an x, I can put 29 minus 6y. Well, in the second equation, there's where my x is. So I'm going to put parentheses, 29 minus 6y minus 4y equals negative 6. It's kind of like composition of functions that we did earlier this year. We plug one into the other. You'll take 29 times 2, and you'll get 58, minus 12y minus 4y equals negative 6. Combine like terms, be careful with signs. That's 58 minus 16y is negative 6. Got to get the y by itself, so I'll subtract 58 from both sides. And I'll get negative 16y equals negative 64. Divide both sides by negative 16, and we get the y value equals to 4. But remember, I'm looking at two lines and I want to know where they cross, so I still need to find the x value. So you could plug it in to one of the equations. It's usually best to go to the original equation, but it would be faster if I went to the one where I have it all isolated by itself. So you can do it there if you want. But for practice, we will go ahead and do what's best, and we'll go back to the original just in case we messed up. And that would be x plus 6 times 4 equals 29. X plus 24 equals 29. Some of you could see it, but if you just need to subtract to find the rest, x is going to equal 5. So the 0.54 is what satisfies both of those equations, and it will be the solution to that system. Now, sometimes things look differently. We can write lines in multiple different ways, and sometimes they kind of make us want to do different things, and that's okay. For example, if the problem looked like this, all three of these are the same. X plus 3y is 14, x plus 3y is 14. This time, the only thing they did different was they moved the 3y over here, but they're all the same. Down here, I have y equals x minus 2. What did they do here? They subtracted x and put it over on the other side, and then they left it the same. If my problem looked like this, it screams, hey, Miss Bruno, why don't you use substitution? And I would. Y is already by itself, so I could plug x minus 2 into this other equation where I see the y. So it'd be x plus 3 times x minus 2, and it will equal 14. Distribute. X plus 3x minus 6 equals 14. 4x minus 6 equals 14. Add the 6 to get 20. 4x equals 20, and x equals 5. Well, we already did this problem earlier. When x is 5, y is 5 minus 2, which is 3. What if it looked like this, though? Would I have wanted to use substitution? No. I have opposites already. I would have used elimination. They already have opposites in the x, so I would just add the two equations. Even though they're the same, the way it looks makes me want to do a different method. The x's are eliminated, and I get 4y equals 12. This time, it was way quicker to get y by itself, and y is 3. Plug it into one of the equations to find x. I'll use the top one. X plus 3 times 3 equals 14. That's x plus 9 equals 14. And x equals 5. So once again, you get the answer, x equals 5, y equals 3. What if it looked like the last equation? I wouldn't want to use elimination right away because it's not lined up. And on this one, x is by itself. So maybe I would plug 14 minus 3y in for x. Now be careful here. Some kids make mistakes. That negative in front of the x means I will have to distribute the negative to both signs here. Kids tend to make mistakes there. It'll change the sign of both, and I get negative 14 plus 3y plus y equals negative 12. Negative 14 plus 4y is negative 12 when I put the y's together. I add 14 to both sides, and I get 4y equals 2. What did I mess up? Negative 14 plus 3y plus y equals negative 2. Negative 14 plus 3y plus y is negative 2. Negative 14 plus 4y is negative 12. Look what I did. I turned a 2 into a 12. Ding, ding, ding. Says Bruno. I was like, why am I not getting the same answer? Negative 2, negative 2. Negative 2 plus 14 is 12. There's the same answer. Divide both sides by 4, and y equals 3. Since y equals 3, I can now find what x is. I'll plug it into the top one. 14 minus 3 times 3, 14 minus 9 is 5, and x equals 5, no matter which way you did it. So one time I substituted for x, one time I substituted for y, and one time I used elimination, and I got the same answer every time. Now, this program is really wanting you to pick wisely what you get rid of, and if you're going to use substitution. They want us to avoid fractions if possible, but that's not important to me. But it is usually easier to work with one equation than the other. If I was going to solve this by substitution, which I might, because there's not opposites, so I would have to do some work anyway. So substitution is a good method here. I do have to go to work. I have to isolate a variable. I'm going to want to work with the bottom equation, because on the top equation, if I get x by itself, I'm going to have to divide by 3, and that gives me a fraction. If I get y by itself, I'll have to divide by 4, which gives me a fraction. On these, if I get x by itself, I'm going to divide by 2, and it's not going to give me a fraction. So I'm going to do that. I'm going to get 2x equal to negative 10y plus 24. And if I get x by itself, by dividing everything by 2, I get x is negative 5y plus 12, which is nice because there's no fraction. Now I can plug it into the other equation. I'll plug it into the top one because that's where the substitution will happen. And I'll get 3 times negative 5y plus 12 plus 4y equals to 3. We'll distribute negative 15y plus 36 plus 4y is 3. Negative 15y and 4y is negative 11y plus 36 equals to 3. If I subtract 36 from both sides, I get negative 11y is negative 33. Divide both sides by negative 11, and I get y equals positive 3. So y is positive 3. Let's go ahead and find x. Well, 2x plus 10 times 3 is 30 equals 24. Subtract 30 from both sides. That's negative 6. So 2x is negative 6, and I'm sorry, I'm out of space. Divide both sides by 2, and I get x equals negative 3. So these two graphs will cross at the point negative 3, 3. That is the solution to the system. Try to make it easy on yourself if you can. So let's look at this. They don't want us to solve the system. They are telling us what the answer is, but they want to know this. If you were going to solve it, what would be the best first step according to the strategy you learned? They want us to use substitution, so that's what we'll use. Which one would I want to use to get a variable by itself? I won't want to use the top one because it will leave us with fractions. I would want to use the bottom one, and I would want to divide by the 5. So I would use the bottom to get x by itself. So I would subtract 10y first and get x by itself. That would be the get x by itself. That would be the strategy I would use so that I don't have to get fractions. It's not wrong to use fractions. It's just usually easier for you if you don't. Now, what about this problem? They suggest multiplying by 3/2 to get rid of the fraction. You can multiply every single piece by 3/2. If you did that, you will get x plus, the 2's will cancel, and you'll get 3y, and the 20 divided by 2 is 10. 10 times 3 is 30. And you can use that instead. I would not have done that. I will not lie. I don't care about fractions as much as they do. I would have gone straight to getting y by itself here, and I would have used y is negative 10x plus 68. Either way is fine. Completely up to you. Yes, I have the 2/3, but again, it doesn't bother me. If it bothers you, clear out the fractions. I will substitute this into this guy. So yeah, I have the 2/3 x, but I'm okay with it. Plus 2 times negative 10x plus 68 equal to 20. Distribute 2/3 x minus 20x plus, well, what is 68 times 2? That's 136 equals to 20. I do have to combine like terms here. If you type 2/3 in your calculator and you subtract 20, you get a decimal. Hit math 1 and you get negative 58 over 3x plus 136 equals 20. Solve from here. Negative 58 over 3x, I have a dead spot in my board here. I don't know if I'll be able to finish this up or not, equals 20 minus 136, that's negative 116. You can divide both sides by negative 58 over 3 or multiply by the reciprocal, negative 3 over 58. And I have negative 116 times negative 3 divided by 58, and I get x equal to 6. If you want to get rid of the fraction, you think that's way easier for you, please do it. But there's also nothing wrong with working with fractions a little bit. Plug in x equals 6, probably into the top one to get the y. 10 times 6 plus y is 68. That's 60 plus y is 68. Subtract 60, and y equals 8. So the point 68 is where those two lines will intersect, and that is the solution to the system. Okay, so here's the summary of all the things that you want to make sure is in your notes. There's some key concepts and the steps to solving, and just a reminder what we did. We solved by substitution.